What's up, AP Psych? It is time to get down and dirty into the biological basis of psychology, and it doesn't get any deep down dirtier than the neuron, which is a brain cell. You can see that there's a ton to learn about the neuron, but here's the good thing about this topic and most of this unit. All you need to do is memorize information. You don't have to interpret a ton. This is the most black and white, yes, no, fact-based, not fact-based, right and wrong based unit that we're going to have. So let's get to it. This is a neuron. Neurons do look a little different depending on where they are in the body and what they do, but they basically have the same structures. So let's learn what those structures are. The first structure is a dendrite. The dendrite are the little end spindly finger things that receive incoming messages in the form of chemicals. I'll talk about those throughout this. In the form of chemicals, chemicals come into the dendrites, they are received, and then that message goes into the cell body, which contains the nucleus. And this nucleus is going to make the decision of do I send off the message or do I stop it here? We call that firing. Does it fire off that message or not? If it does, that message is going to travel down the length of an axon. So it's this whole pathway, the whole electrical pathway that the message would go down, which is covered in something called the myelin sheath. This is fatty tissue that insulates the axon and speeds up the transmission of the message, meaning if this nucleus decides to fire, it's going to go zoom all the way down that axon really, really fast as it can without stopping. And then if it makes it that far, it's going to reach the axon terminal buds. These are the endpoints of a neuron. They release those chemicals I was talking about. You'll see that they're called neurotransmitters. All across our notes, you'll see we have NTs, neurotransmitters. These are chemicals in our brain, and it will fire off these chemicals across the synapse, which is just a gap. More on that in a little bit, sending that message on to the next neuron. So put it all together and you have an electrochemical system. There's an electric signal that gets sent down the axon, and then the message is sent off to the next neuron in the form of chemicals called neurotransmitters. So there you go. You just learned something already. You and your body is a giant electrochemical system. Wow. Besides the parts itself, the most important thing you need to learn about a neuron is the neural firing process or transmitting a message. Now, just so you understand what it means, it's basically a message is going to your brain to tell your body to do something. A message might be sent up from your stomach because you're hungry. A message might be, oh, I just pinched my finger in this drawer that you can't see and I need to move my finger. Or the message might be to do nothing. Just sit there. Okay, so all these messages that are telling our body what to think, how to feel, what to do all the time are always happening between neurons. So let's talk about the phases and the steps of this process. The first step is the most chill one. It's the resting potential. The neuron is at rest, at resting potential. Clever, huh? It's at homeostasis, meaning it is fine. It is not firing. It is not recharging. It's just there. It's at rest. There's a positive charge on the outside of the neuron and a negative charge inside the neuron. I suggest you draw something that looks like this. And we have polarization. Think of the idea of polar opposites. When some people are polar opposites or magnets are polar opposites, they stay away from each other. And as long as they stay away from each other, nothing bad happens. It just chills. So opposite ions are calmly kept away from each other. But then sometimes a message does need to go through. And that message would be in the form of neurotransmitters. We will define that later in your notes. Stay with me. Neurotransmitters might be sent from one neuron to a next. So let's say I pinched my finger in my desk drawer underneath me. The message is going to go from the neurons in my finger to the neurons in my hand, to the neurons in my arms, to my spine, to my brain to say, move your hand. And so that might be an excitatory signal. It's a message telling me to do something. So excitatory or inhibitory signals are sent depending on which neurotransmitter it is. And then it goes to that nucleus, and the nucleus will determine, are there more excitatory signals or are there more inhibitory signals? If there's more excitatory signals, it will tell that message to fire, to keep going, take action, and go down the axon and send that message to the next neuron. If there's more inhibitory signals going through, then nothing will happen. That neuron will not continue to send the message. It will just stop doing anything. It will stay at rest. So, in other words, if excitatory signals are greater than inhibitory signals, a threshold is reached. You get enough excitement in that neuron, so to speak, that action potential will happen. And action potential means a neuron is firing. An electrical nerve pulse, which is really that message that I'm talking about, is sent from the nucleus down the length of the axon. So, chemicals in the form of neurotransmitters sending a message. If it's excitatory enough, an electric pulse goes down that axon all the way down till the end. Boop, like my fancy arrow. If it fires, it has to go in an all or nothing kind of way, meaning it maintains that message maintains the same intensity down the entire length of the axon. The strength of the message, the power of the message, the speed of the message comes all the way through. You can kind of think about it like, I don't know, throwing a ball or firing a gun, because that once you do it, once you throw it, it's going to, or once you fire it, it's going to go all the way through. There's no stopping and turning around. We also call action potential depolarization. This is just another word for the neuron being action. A domino effect of opposite ions seem to chase one another down the axon, and it's like semi-permeable, so these things come in and out like these gates, these ions come in and out the axon, up and down, and they kind of chase each other, and that's what's creating the action. Positive ions are coming in, causing the negative ions to rush out because they do not mix well at all. And then after the firing, there's a refractory period where the neuron resets. It's almost like it needs to recharge. After firing, the neuron is focused on resetting and therefore unable to fire again. So we need to get back to that position of polarization where the positives and negatives are back on the correct side, not mixing and not creating action. And that's it. Those are the three major phases of a neuron's day-to-day activities. It's at rest in the resting potential and it's polarized. Then if it's going to fire, it goes into action potential mode of depolarizing at an all or nothing kind of way. And then it needs to enter a refractory period before it can rest or fire again. Okay. Now, one thing, not one more thing. I have plenty more to say. One thing I had mentioned about, I'll explain it later, is the concept of a synapse. The synapse is this space right here. So if we imagine the sending neuron, the action terminal buds, has a whole bunch of neurotransmitters sitting in it. These are those chemicals that I kept saying, we'll define it. Well, we're defining it right now. These are chemical substances that cross the synapse to carry the message to the next neuron. So action potentials come down the axon to the axon terminal buds and says, fire, message needs to go, go, go. The neurotransmitters cross the synapse or the synaptic gap, which is just this space, open space between two neurons, to the receptor sites on the dendrites of the other neuron, the one that's going to receive the message. So receptor sites, specific points on dendrites that receive specific types of neurotransmitters. So each receptor site is designed to get a certain neurotransmitter, like certain ones are designed for dopamine, certain ones are designed to receive serotonin, and so on. The synapse is simply a gap, not a part of the actual firing. It's just the gap that the neurotransmitter has to cross. If the neurotransmitters cross that synapse, they are either received on the receptor sites or go through reuptake. So each receptor site can only hold, let's just say, one chemical. not sure that that's entirely true, but each one, think of it like a parking space where each neurotransmitter has to find a receptor site or a parking spot. And if they get all full, they turn around and go back home. That's reuptake. So if they're received, the neurotransmitters bind to the receptor sites on the receiving neuron's dendrites, or they go through reuptake where the extra neurotransmitters are reabsorbed back into the sending neuron. Oh, mentally scratch out the word by, or just are reabsorbed back into the sending neuron. So sent out through the axon terminal buds, received on the dendrites, if not, goes back into the axon terminal buds to hang out in these vesicles, these little pockets, to wait for the next time that that message might be fired or a similar message is fired and that chemical needs to be sent over again. Sometimes sending that message isn't so easy for the body and something breaks down and disrupts that process. Two examples of what could happen are myasthenia gravis. My gosh, I just practiced 4 times before I hit record. Still hard for me to say. This is a neuromuscular disease. It's essentially causing extreme muscle weakness. So acetylcholine receptors, which is going to be one of our neurotransmitters, acetylcholine receptors are blocked. And without that neurotransmitter, the muscles can't contract. So your muscles get very weak very quickly. This is considered an autoimmune condition. And some examples that I've read about might be where a person wakes up feeling okay, and then through ordinary things like chopping food while cooking, that person feels very weak and tired. Or maybe if it affects the muscles in their eyes start to droop because those muscles aren't contracting like they should, and the person has extreme muscle weakness. Another one is MS or multiple sclerosis. This is when the immune system attacks the myelin sheath. Remember what we said the myelin sheath does? Do you remember? Check your notes. It helps protect and speed up the transmission of that message down the axon. And so if the immune system starts attacking the myelin sheath, it can cause communication problems between the central nervous system, which is where the brain is, we'll learn that in the next lecture, and the rest of the body. So if the messages can't go between the brain and the rest of the body, you might experience numbness in the limbs, lack of coordination, ability to walk, because what's happening is it is deteriorating or breaking down the nerve fibers. Like it's essentially breaking down your neurons. Nerves, neurons, all the same thing. Okay, I keep saying, I'll tell you about neurotransmitters. I'll tell you about neurotransmitters. Well, here I am telling you about neurotransmitters. I'm going to go through each one. You'll see that I already gave them to you in your notes, but you still must memorize what they do. Acetylcholine, like I just said, is in charge of muscle contractions. It's also involved with memory and learning. If you have too much or too little, you might result in Alzheimer's disease or paralysis. Dopamine is in charge of movement, are largely responsible for movement, the thought process, and your reward sensation. So like that feeling of, ooh, I just had a peanut butter cup. Ooh, it's my lucky day. Or, ooh, I just finished my homework. Thank goodness. Anything that kind of makes you feel that little pump of being like accomplished or having gotten something. Having too much or too little could result in Parkinson's, schizophrenia, or addiction. Now, I'm not saying it could be too much or too little. Some of these are too much, some of these are too little. I'm just kind of grouping them all together. Serotonin is vital for our emotional states and mood regulation, like keeping our moods stable. If we have too much or too little, we might experience depression, sleep disorders, or aggression. Norepinephrine, I want you to add a little note to yourself that this is like adrenaline. It has to do with physical arousal, like pumping you up to respond to a situation, learning and memory. Too much or too little also contributes to depression, anxiety, and stress. GABA is an inhibiting, remember inhibitory signals, remember that from before? It's an inhibiting neurotransmitter, and it will slow down the sending of messages or stop them, and contributes to your sense of relaxation, calm, and especially sleep. Not having enough or having too much contributes to anxiety disorders and Huntington's disease. Endorphins are your body's natural painkillers. Write that down. So they are involved with pain perception, pleasure, and they are released with exercise. So we associate them with that runner's high. It's not necessarily required to, it doesn't necessarily happen just with running. Anytime you work out a lot or you're exuding a lot of energy and at first it feels really hard, but then you just feel like incredible, like I could do this forever. It's because your body released endorphins and it makes you feel really good. It's also associated with opiate addiction. And then glutamate is involved with learning, memory, and makes GABA. Here's what's interesting. It is the most abundant excitatory neurotransmitter. So it being excitatory from a series of events results in the creation of one of our inhibitory neurotransmitters. And this one, having too much or too little, can result in insomnia, seizures, migraines, or also Huntington's disease, which makes sense that GABA and glutamate influence each other. Now be careful because just because I gave you all this information doesn't mean you should just look at it and move on. You are responsible for memorizing these. The good news is we will talk about so many of these throughout the entire course that you'll kind of naturally start to learn them that way too. Okay. One last topic is the difference between neurotransmitters and hormones. I know that you've heard of hormones, but you might be new to neurotransmitters. You might have heard of some of those things on the previous slide, but you never knew what a neurotransmitter was. These act in similar ways. Both neurotransmitters and hormones send messages through our body. They just do it in different ways. Neurotransmitters travel through the nervous system using the neurons, and their messages are often sent, or not often, are always sent fast, but also only last a short term. Hormones are sent through the bloodstream via the endocrine system. And we're not going to learn a lot about that, other to say that it is in charge of releasing hormones and sending them through our body. But hormones travel very slowly and then they linger a long time. An example of how they work together, because, oh, wait, I got one more little reveal here that my little face bubble is blocking. The endocrine system finishes what the nervous system starts. So, for example, imagine we stubbed our toes. The neurotransmitters will very quickly send a pain signal to our brain, and it will make us, on purpose, feel pain wait for it, through endorphins, saying, ow, ow, ow. And it makes us feel like a little bit of adrenaline too. We know it hurts. And so that message gets sent through our neurons to our brain. And then in our brain, the pituitary gland, more on that in the 2 lectures, will send a message to the endocrine system saying, release hormones to make us feel pain a little bit longer. It needs to linger. Or if you think about another example of if you get mad, anger might be a message sent through neurotransmitters, but even when the thing that you're mad about goes away, that feeling sometimes takes a while to go away. That's because the hormones were released when you were angry too, and they take a little bit longer to fade from your body. Okay, that's all about the neuron, neurotransmitters with a teeny tiny touch of hormones at the end. All right, see you at the next one.